This is Jack Jackson back again. We're continuing to look at some derivative problems. That graph is from the last one. And here's the problem that we'd like you to work on right here. Okay, so this problem says the derivative of the function 5x times e to the 2x. See if you haven't worked that one already, go ahead and work it now. Press pause. Okay, well, first thing we can do is think of the constant multiple rule and bring the 5 out front of the derivative sign. Then we have a product of two things. One of the first one we'll just call is just x. The second factor is e to the u, where u is the 2x. So we're eventually going to be using some chain rule here on that one. All right. Okay, now the 5 is out front, so don't forget the parentheses around the whole thing. Then within this, we're going to use the product rule, which says it's the first times the derivative of the second plus the second times the derivative of the first. So each of these factors gets a derivative, and just like it is, multiplied together. And then you add those two things. That's what we have here. Now the derivative of e to the u is e to the u, but this is the derivative with respect to x, and that's u. We've done a substitution, so the substitution rule, i.e. the chain rule, applies, and so we have to also multiply in our chain the derivative of the u. Here we have e to the u, and then the derivative of the x is just 1. So here we have, we still have the 5. So when you're writing these, be sure you write your equals down. Be sure you write everything down that doesn't change. So write down the 5, the parentheses, and so forth. The plus, this is e to the u. 1 times e to the u is e to the u. And so here we're taking the derivative of the u. U is 2x, so the derivative of that 2x is just 2. And so these both have an e to the u, which I can factor out, and I went ahead and did the substitution. U is 2x. So out front we have a 5, an e to the u, or e to the 2x. And what's left inside? Well, that e to the u cancels. We got a 2 times the x, which is 2x. And that one cancels and just gives us 1. If we were to distribute this out here, of course, we would be back at this point here. And so there is the first derivative. Okay? Now let's do another one. Let's do the second derivative of this function. Go ahead and work that out and come back whenever you're finished. Press pause now. Okay, before we go on to do the second derivative, let's go ahead and check this with the calculator. And the way we can do this with our calculator is we put our original function in y1, 5x, e to the power, parentheses, 2x. And this is the older operating system on a TI-84. We put in numerical derivative, which is math 8. Here, I'll do the whole thing out for you. I leave mine in there so I don't have to redo this every time. But if you do this once, math, and then number 8, numerical derivative. y1, you can get by variables. Right arrow to y variables, choose function, and then y1, comma, x is your variable, comma, that's like the dx. And then x is evaluated at an arbitrary x, so this will be the derivative function. Actually, it'll be the symmetric difference quotients, but it'll be approximating the derivative function. Now, the actual derivative function is what you found, or what we found, 5 e to the power 2x times, parentheses, 2x plus 1. Now, if we did this right, the table for y2 and y3 should agree. I can actually toggle off the table for y1. Don't delete it or y2 won't work right. But now we do this. So the original function goes in y1. Leave y2 set up like this all the time. And here's what y3 looks like. In the newer operating system, this will look like this. For y2 would look like just like you'd write it, d over d, and in this box you put x, in this box you put y1, and then it'll be such that once you put the x in this one, this will say x equals, and in this box you also put x. so it looks just like you write it. This is how you do it on a TI Inspire or on a newer operating system on the TI-84. Now let's check and see if this works out. Let's look at our table. And sure enough, it looks like things are matching up quite nicely. Now, of course, if you put your cursor over here, look at the digits way down here in this part of the thing, you may see some differences. But notice it's way over in the digits. So, of course, that's the reason why they're not perfectly the same, is Y2 is an approximation. It's a symmetric difference quotient. Y3 is the actual value. But at least to the digits that we have in the table and more, they actually do agree. They agree at lots of places. This gives us a lot of confidence that we have the correct value there. Okay, I'm going to actually pull that over here and also pull this over here as well. Okay. So now let's take a look at the second derivative. Okay. Now, hopefully you've already done this one as well. So now, once again, I can bring the 5 out front, and I have a derivative of a product. So it's very similar to the last one, actually. We still have an e to the u, where u is 2x, just like we had before. And instead of an x here, we have a 2x plus 1. So it's very similar to the first derivative. The 5 is still out front. We have parentheses around the whole thing here. And then here we have the product rule. So it's the first, e to the u, times the derivative of the second. That's the derivative of the 2x plus 1. Plus the second factor, 2x plus 1, times the derivative of the first factor, e to the u. Now, derivative of e to the u is e to the u times the derivative of the u. The derivative of 2x plus 1 is just 2. The rest of the stuff was just copied straight down. When I do this, I will copy these things down first and then make the changes of the parts that need to be changed. U is 2x, so that derivative is just 2. Now, if you look, these both have a 2 and they both have an e to the u. I'm going to factor that out. The 2 times the 5 is the 10, and we have our e to the u. Now, what's left? Well, this divided by 2 e to the u is 1. And when this cancels out, we get 2x plus 1. Well, 2x plus 1 plus 1 more is 2x plus 2. So I can actually factor out another 2, making this 20 e to the u x plus 1. And then e to the u, of course, u is 2x. So this is 20 e to the 2x times x plus 1. While we're at it, let's check that one on our calculator. So to check that one, we want to put our original, which is actually what's in Y3. Actually, you know what? Save myself a little time here. Let's do it this way. Let it be the same as Y3. And then I don't need to see that one, that one. And then the derivative of that is going to be this one here. 20 e to the power parentheses 2x close parentheses times parentheses x plus 1. Okay, so if I've got all that in there correctly, and look at the tables, now these should match. They do. Notice here on this one, it may not look at first glance like it matches here at -1, but it does actually. This is e negative 6 means times 10 to the negative 6. So this has 0.5 zeros and then a 1/8. The actual answer is 0. That agrees to 5 decimal places. So certainly this looks pretty good. Okay, bring that over here too, and then bring this over as well. Okay, now, what else were we wanting to do here? Well, one of the things that we wanted to do was to, okay, here we are. So we have the formula for the first and second derivative, and of course the original function. We want to find the equation of the tangent line, when x is 1. So to do that, we take the original function, way up here, and put in a 1 for x. So it's 5 times 1 times e to the 2 times 1, right here, which is just 5e squared. Then we take the derivatives and put in x is 1 there. So this is 5e to the 2 times 1 over 2 times, or times 2 times 1 plus 1. That looks right there. So 2 times 1 is 2 plus 1 is 3, times that 5 is 15. And again, we get e squared. So it's 5e squared and 15e squared. The f prime of 1 is the slope, so that goes right here. So it's y, or t of x, equals the slope, which is f prime evaluated at 1, 15e squared. Then x minus the x value we're evaluating at, which is 1. And then the y value that we're evaluating the function at, which is 5e squared. So what we know is the point 1, 5e squared, 1 comma 5e squared, is both on the tangent line and on the original function. And at that point, the tangent line has a slope of 15e squared. Now let's graph all those together, and using the same color scheme that we've been using, you can see the original function in blue, the derivative in red, and the second derivative in, no, the derivative is in green and the second derivative is in red. And the purple is the tangent line. So we see when x is 1, we see them touching each other there. And if you did 5e squared, that's going to be the y value where these two graphs touch, right in here. Okay, and so you see that they touch at the right point. There, you can tell it's a tangent line because if we were to zoom in here close, right in here, they look the same. The graph of the tangent line and the original function look very similar. Let's leave some other characteristics we may notice. Well, it looks like the derivative crosses the x-axis right here, somewhere near negative 0.3, somewhere in that vicinity, and that's going to be when the original function has a minimum. So about here we have a minimum. From there on, the original function, the derivative is positive, and the second derivative is positive, so the function is increasing concave up from there on. It crosses here at 0. Actually, I know I said negative 0.3, but we know exactly what it is. It's negative. Actually, it's negative 1/2 is where the derivative crosses. Yes, that is negative 1/2. Exactly. And the second derivative is 0 when x is negative 1. You can see that right here. This part's always positive. This part's 0 only when x is negative 1. So in fact, that is exactly negative 1 there. That's an inflection point on the original function and a minimum on the derivative. So the derivative has a minimum right there, an inflection point right there on the blue original graph. So this one's concave down, decreasing, then it hits an inflection point, so it's still decreasing but concave up. It's a minimum. Now it's increasing concave up from there on out. Okay, so I think that's a pretty good description of that particular function. Come back next video for some more examples where we'll do this one right here. In fact, if you want to write this one down before you even come back for the next video and work it, that would be a good idea.